Good day, welcome my dear students to the 9th lecture of Mechanics of Solids. In the last lecture we discussed about transformation of stress and strain. So for the transformation, by the transformation method we can transform a different stress values on the reference planes into another planes which are at an angle theta with the reference plane. So we learn different equations for the transformations. Using this equation we can calculate the normal stress, shear stress on an arbitrary plane or an inclined plane, and also we can calculate the position of the principal plane and the value of the principal stress, major and minor principal stress. Then we calculated we derived the formula for finding the maximum shear stress and the normal stress on the maximum shear stress. Okay, using these 8 formulas we can calculate the normal stress or shear stress on any plane. By the orientation of the reference plane we can calculate the stress components on any plane that is at an angle theta with the reference planes. So that is a theoretical one, and the same transformations can be, or the transformation component of stress can be calculated using graphical method. Instead of using that 8 formula for the calculation, here we use graphical method. So that graphical method is known as Mos Circle. Okay, so the stress components on any inclined plane can be easily found out with the help of this geometrical construction that is called Mos Circle. So in the last lecture we discussed a plane stress condition. So this is our body, and this is subjected to some normal stress sigma x, sigma y, and some shear stress tau xy, tau xy, tau xy, tau xy. These are the normal stress and shear stress acting on this body. And in this body there is an inclined plane. This is an inclined plane. This is an inclined plane. That inclined plane is at an angle theta with this vertical plane. So we can give values for B, D, A, this is C. Okay, so we can give value for the represent the coordinates with the A, B, D, C. So this is the inclined plane. That inclined plane make angle theta with the BD plane. And here in this inclined plane a normal stress is acting, or a normal stress is developed. We can say that is equal to sigma n. Sigma n is the normal stress. And shear stress is developed. That is, we can give sigma t or tau. We can give any value. So this is equal to sigma t. Sigma t. That is the shear stress acting on that inclined plane. So we have 8 formulas to 2 formulas, sigma n. For calculating sigma n we have formula sigma x plus sigma n is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta plus tau x by into sin 2 theta. This is the formula to calculate the sigma n, where theta is this angle. Sigma t can be calculated using sigma x minus sigma y by 2 into sin 2 theta minus tau x by into cos 2 theta. This is the formula for calculating the sigma t. Okay. And the graphical method, that is called Mos Circle method, Instead of using this formula, we can calculate the sigma n and the sigma 2, and we can give this this is as E. This plane name is EF plane. Okay, so in the graphical method we have two axes, x-axis and y-axis, and this is the positive x dash and this is the positive y dash. Okay, and in this, first I am representing this BD plane and CD plane, because in BD plane we can see this plane is in between this BD and CD plane. So next I am going to represent BD plane and AB plane. These are the two planes I am going to represent on this Mos Circle. So this is a graphical method, so we should use a graph to draw this Mos Circle. So this is the origin, the x dash representing normal stress. So in the x dash it is a normal stress dash, and the y dash representing the shear stress. Okay, y dash representing shear stress. So all the normal stress should represent in the x dash, all the shear stress should represent in the y dash, and this is the positive y dash, this is the positive x dash. So all positive or tensile, we take tensile stress as positive, so all the tensile normal stress should draw in the towards the right side, and in this opposite direction the normal stress which is compressive is represented in the negative x dash, and similarly the negative shear stress represented in the downward dash. So next I am going to represent this BD plane. In the BD plane we have two stress sigma x and tau xy. So sigma x is a normal stress, so we should represent sigma x along the x dash. So for example, if the sigma x is equal to 100 Newton per meter square, take appropriate scale for this. For drawing Mos Circle we should take, this is a graphical method, so we should take an appropriate scale. So I am taking 1 centimeter is equal to 10 Newton per meter square. So here we have 100 Newton per meter square, so the total length will be 10 centimeter. Okay, so mark a point, here. This is the point that is equal to 10 centimeter. That is equal to sigma x. Okay, because 110 centimeter is equal to 10 Newton per meter square, but here it is 100 Newton per meter square, and this is a tensile in nature. That is why we represent in the positive x dash, which is a normal tensile. Then in the same plane, BD plane, we have tau xy. So for example, tau xy value is equal to, for example, it is equal to 30 Newton per meter square. Then when it is on the scale, how much centimeter? 1 centimeter is equal to 10 Newton per meter square. Then 30 Newton per meter square will be 3 centimeter. So, and the tau xy, that is shear stress should be either in the positive y dash or in the negative y direction. And the direction of this tau xy is based on the moment. This is the center of this body. This is the center of this body. And this is the tau xy is in the upward direction. Take the moment of this tau xy with respect to the center. So the moment will be anti-clockwise moment. Here it is a anti-clockwise moment. Okay. So one thing. Sorry, this is not the direction. This is the direction of tau xy. This is the direction of tau xy. So this is the tau xy direction is downward. So with respect to the center, what is the moment of this tau xy? This will be a clockwise moment with respect to center. Okay. So clockwise moment of the shear stress with respect to center is taken as positive. That is the sign convention. So we should draw this positive tau xy in the positive y direction, because y direction representing the shear stress. And we know this tau xy is acting on BD. So the next point will be from here. This is take 3 centimeter in the positive y direction. 3 centimeter, because here it is 30 Newton per meter square. So that is equivalent to 3 centimeter. So this is the tau xy. That is 3 centimeter. That is the tau xy. And we got a point. This is a point. And this point representing the plane BD, the stress system in the plane BD. This point representing the stress system in the plane BD, because in the BD plane there are two stress, sigma x and tau xy. Sigma x is represented in the x direction, tau xy is represented in the positive y direction. So sign convention is this is tensile, so positive x direction. This is making a clockwise movement with respect to center, so it is a positive shear stress. So this point representing a BD plane. Similarly, I am going to represent this BA plane. BA plane. In the BA plane, we have sigma y. Sigma y. Sigma y is also a tensile one. For example, sigma y value is equal to 50 Newton per or 20 Newton per meter square. 20 Newton per meter square. Sigma y. So 20 Newton per meter square is equivalent to 2 centimeter. And this is a tensile one, sigma y. So in the positive x direction, we should mark sigma y. So this is sigma y. That is equal to 20 equivalent 2 centimeter. So this is equal to 2 centimeter. That is the sigma y. Okay, we got this point. And again, in the this is not the direction, tau xy. This is the tau xy direction. And next one is tau xy. The another stress acting on AB is another stress acting on the AB is tau xy. And if you check the direction of movement, we can say the tau xy making anti-clockwise movement with respect to center. Tau xy making anti-clockwise movement with respect to center. So Anti-clockwise movement with respect to center is taken as negative shear stress. So in this, from this point, draw a line. For example, tau xy equal to, this will be same, the entire in a plane stress condition, all the four faces subjected to same shear stress, tau xy. We already discussed about equivalent cross shear, tau xy equal to tau yx. Cross shears are equal. So here actually it is tau xy or tau yx, but all are equal by applying the equality of cross shear. So this will be also equal to 30 centimeter, so 30 Newton per meter square. So this is equal to 3 centimeter, but the direction is different. Direction is anti-clockwise, so it will be in the downward direction. Anti-clockwise is taken as negative. So draw a line equal to 3 centimeter and mark a point. And this point representing the plane AB. This point representing plane AB, because in this point, what is the normal stress? This is a normal stress, that is equal to sigma y. Sigma y is the normal stress acting on AB. And what is the shear stress? Shear stress is equal to tau xy. This one. This is tau xy. So we got these 2 points. And then find out the bisect of these two points. The middle point of this line. So this one will be the bisect of these 2 points or this line. Okay, this is the point. We can represent this point as C. Then draw a circle with the C as center, and diameter as, and then draw a line connecting these 2 points. So this line will be passing through C. Okay. Because these 2 lines length are equal, so of course this line will be passing through the center between these 2 points. Okay. Then draw a circle with the C as center, and these 2 points as diameter, this line as diameter. So then draw a circle. Okay, for this circle, this C is center and this line is the diameter. We can draw a circle. We can draw this circle. And this circle is called Mohr circle. This circle is called Mohr circle. Okay, so we already represent these 2 planes. That next we are going to represent this inclined plane on this Mohr circle. So from this it is clear that the 2 points, the 2 planes AB and BD planes are represented as the 2 points on the Mohr circle. AB and BD planes are represented as the 2 points on the Mohr circle. Or we can say any plane passing through this point D will be a point on the Mohr circle. Okay, any plane in this system will be a point on the Mohr circle. So this DE plane also will be a point on the Mohr circle. Or this DC plane will be a point on this Mohr circle. So any plane on this system will be a point on the Mohr circle. It may be this point or it may be this point. So next we are going to represent this DE plane. Okay, and from this it is clear that this DE plane is at an angle theta from the BD plane. And how this, by the rotation of this BD plane by an angle theta in clockwise direction. This is the clockwise direction, right? By the rotation of BD plane by an angle theta in clockwise direction, we got this DE plane. Similar concept can be applied here. Similar concept can be applied here. But here we can see what is the angle between DB and BA. It is 90 degree. Between these two planes, the angle between BD and AB is 90 degree. But here what is the angle between these two planes? This is my BD plane, this is my AB plane. The angle between these two planes are 180. That means any angle in this system should be multiplied by with the 2 when it is representing on a Mohr circle. Any angle in this system should multiply with the 2, or the angle value is doubled when it is representing on a Mohr circle. So here the BD is rotated by an angle theta in clockwise direction to get this DE plane. So to represent this DE plane from the BD, we should move clockwise direction, because here it is clockwise. So here move in clockwise direction by an angle 2 theta. Here it is theta, but here it is doubled and it is 2 theta. So by the rotation of BD angle, because here for DE is from BD, it is rotated by an angle theta in clockwise direction. So from this is the point representing BD and this is the line representing BD. So from BD rotate 2 theta, double that of the theta in clockwise direction, and draw a line, and this point representing this ED plane. This is the ED plane. Okay, this is the ED plane. Then what is the normal stress on ED plane? What is the normal stress on BD plane? That is this much from O to BD, that is sigma x. What is the shear stress of BD plane? This distance, right? Similarly, for ED plane, this will be the value of shear stress, and this will be the value of normal stress. This is normal stress of ED plane, and this is shear stress of the BD plane. This normal stress and shear stress. So take a scale and measure this length, and if it is, for example, if this is equal to 2 centimeter, 2 centimeter is equal to 20 Newton per meter square. So sigma T is equal to 20 Newton per meter square. Then again measure this length, measure this length, and for example, if it is 9 centimeter, sorry, 10 centimeter, sorry, 11 centimeter. Already sigma x is 10 centimeter, so this will be higher than 10 centimeter. For example, this is 11 centimeter. Then 11 centimeter is equal to 11 into 10, 110 Newton per meter square. Sigma n is equal to 110 Newton per meter square. So by this way we can calculate, or we can find the normal stress and shear stress on any plane inclined at an angle with the vertical or horizontal. For example, if you want to find the another plane, for example, take this plane. Take this plane. Okay, this plane. That is at an angle alpha with the vertical. Alpha. Okay. In clockwise direction from BD, move in clockwise direction by an angle alpha, we got this plane. So how can we represent this plane? From BD, here it is alpha in clockwise direction, here it should be 2 alpha, 2 into alpha in clockwise direction. Then draw a line here, draw a line here. This is the point representing that plane, and this length will be equal to sigma x, and this length is the shear stress. Okay. So similarly we can draw any plane using this Mos Circle. The next question is, so already I said any plane on this system will be a point on the Mos Circle. So here we can see this is this plane, ED plane is this point on the Mos Circle. Okay, will be a point on the Mos Circle. Then what is the point of the principal plane? The point on the Mos Circle which represent principal plane. What are the conditions for principal plane? For a principal plane, normal stress will be maximum or normal stress will be minimum, and one more condition, the shear stress equal to 0. This is the condition for principal plane. And out of this infinite number of points on the circle, what are the points which satisfy these two conditions? Sigma n is maximum, sigma n is minimum. First one is major principal plane. That is sigma n is maximum, tau is equal to 0. What is the point corresponding to this condition? Here we can see tau is the vertical distance from this axis to vertical distance, that is a tau, right? Downward or upward vertical distances. If you take this point, for example, maybe this is the principal plane. See this, there is a shear stress value. So this is not a principal plane. If you take this plane, this point, there is a shear stress value. So this is not a principal plane. Then from in what point this value is equal to 0? This value is 0 in this point. In this point, you can see in this point there is no vertical distance from x. So this is the point where shear stress is equal to 0. There is one more point where shear stress is equal to 0, that is this point. This point. So we got 2 points, shear stress is equal to 0. One more condition, sigma n is maximum. What is sigma n? Sigma n is measured along the x direction from origin. So here we represent sigma x, here represent sigma y. So that is the distance from origin to in the positive x direction or negative x direction. So where the sigma n is maximum on this Mos Circle? On this point. Because here if you take this point, this is the sigma n. If you take this point, this is the sigma n, and sigma n is maximum at this point. So this point will be the major principal plane, representing major principal plane. And where is sigma n minimum? This point, because this is the point where sigma n is minimum. This distance is minimum. O to this point is the minimum normal distance. So this point representing the minor principal plane. And what is the minor principal stress? Sigma 2. This is the minor principal stress. This distance into, for example, this distance is equal to 5 centimeter, 5 into 10. That is the minimum principal stress. Maximum principal stress is equal to, take this distance. Take this distance, for example, that is equal to 12, 12 into 10. 12 centimeter, 12 into 10. That is equal to 120. That is the major principal stress value. Okay. And one more thing. What is the maximum shear stress plane? Maximum shear stress plane. So we got major principal plane, minor principal plane. We have one more plane. What is that? Maximum shear stress plane. Where is the location of maximum shear stress plane? On the maximum shear stress plane, shear stress is maximum. That is the condition for maximum shear stress plane. Where is shear stress maximum? If you take this point, this much is the shear stress. If you take this point, this much is the shear stress. If you take this point from the origin to this is the maximum distance possible. Maximum vertical distance. From origin to this circle, this point of the circle. That is the maximum distance. All other points, we can see all the other points, the shear stress, because the vertical distance representing the shear stress. From this x-axis, how much is the vertical distance? That is representing the shear stress, and that shear stress will be maximum between this origin and between the center of the circle and this point. So this is the point representing maximum shear stress, or the plane representing maximum shear stress. And what is the maximum shear stress? This is the maximum sigma T maximum. This is the maximum shear stress. Then one more question. What is the normal stress on a plane of maximum shear stress? We already developed an equation. Sigma x plus sigma y by 2 is the normal stress on a plane of maximum shear stress. So this is the plane of maximum shear stress. Just to calculate this distance. This distance. And this distance is the normal stress on a plane of maximum shear stress. And this will be sigma x plus sigma y by 2. We can calculate that. We can calculate that. For example, what is this distance? This distance is equal to, this distance is equal to this distance, sigma y. And so sigma y plus, I don't know this distance, x equal to sigma n. Okay, this distance plus this distance equal to sigma n. Next is, what is x? X equal to this distance. How much is this diameter? What is the diameter? Up to this, this distance is sigma x, and this distance is sigma y. So this distance will be in between sigma x and sigma y. This distance will be sigma x plus sigma y by 2. Sigma x minus sigma y by 2. That is this distance, half of this distance. Okay, this distance is equal to sigma xm minus sigma y by 2. That distance plus sigma y equal to sigma n. That is equal to, this is equal to sigma xa plus sigma y by 2. So this is about Mohr circle. All the 8 equations, the result from the all 8 equations can be calculated graphically. That is the use of Mos Circle. Next we will do an example. All stresses are in Newton per mm square. Shear stress is acting. That is equal to 25 Newton per mm square. Tau x by all shear stress are 25 Newton per mm square. So the question is to calculate the normal stress and shear stress on a plane. Then angle 45 with this. So here I am taking, this is A, B, C, D. Okay. This is E, plane E. So in this, this is my origin. First we have BC plane. We are representing BC plane. I am taking 1 centimeter is equal to 10. 1 centimeter is equal to 10 Newton per mm square. So here 65 Newton per mm square. So for a BC plane, this distance is equal to 6.5 centimeter. 6.5 centimeter, that is equal to sigma x, 65. Okay, so we got this point. This is tensile in nature, so that is towards the right side. And in the BC plane we have 25 tangential stress about the center. This is clockwise. Clockwise is taken as positive. So we take another length. Okay, that is equal to 25. So we got this point representing BC plane. BC plane. Similarly, the next, this plane, inclined plane cutting DC. So that is why we take DC for next representation. For DC plane we have 35. So with respect to 35 we have, this is 3.5, 35 centimeter. We take 3.5 centimeter, mark this point, and in BC, this is the direction of shear stress. With respect to center, it is anti-clockwise in direction, anti-clockwise downward direction. So this is downward. We got this point, and this point representing BC plane. And draw a line connecting these 2 points. This will be the center of this line, and this point as center. This is its diameter. Draw a circle. Okay, draw a circle. This is the Mohr circle. Next we are going to represent in this BC plane. In the BC plane, actually this is the inclined plane. We are going to find out the normal stress and shear stress on this BE plane. And we know this BE plane at an angle 45 degree clockwise. This is clockwise rotation from BC. 45 degree clockwise from BC. From BC 45 degree. We got B. So this is the BC plane. This is the line representing BC plane. So here it is clockwise 45. Then here it will be 90 degree clockwise. So this is the point 90 degree. Draw a line for 90 degree and we got this point. This is the BE plane. BE plane. So this is the BE plane, and we can calculate the normal stress on the BE plane. And this distance, measure this distance, and here this distance will be 7.5. This distance will be 7.5. So 7.5 into 10, 75. So sigma n is equal to 75 Newton per square. Measure this distance using scale. So we got 7.5 into 10, 75. Then measure this distance. Using measuring scale, and after that we will get it is as 1.5. It will be 1.5. So sigma T will be 15 Newton per 1.5 into 10, 50 Newton per mm square. So we got the shear stress on this plane. Then for the calculation of the principal stress, this is the principal plane. These are the two principal plane. Measure this distance from the origin to this point. And after measuring, we got a particular value. That into 10 is the major principal stress. Measure this distance, origin to this point. For example, this is equal to y. Y into 10 will be the minor principal stress. For the location of the principal stress, this is the point representing the principal stress. And this is a line connecting this point and the origin. Measure this angle. For example, this angle is equal to theta. This angle is equal to theta. This theta, here we know what the angle here in this system. We represent the double of that angle in the Mos Circle. So if you take any angle from the Mos Circle, we should take the half of that angle here. If you take theta here, if you measure theta here, we should convert we should use the half of that angle here, because what we take from here is doubled here. So what we take from here should be half here. So if we got it is as theta, and here we can see from BC by clockwise rotation we got we come to the point principal plane, point of principal plane by the clockwise rotation from BC. This is the clockwise rotation. Okay, by the clockwise rotation from BC. So from BC theta angle clockwise rotation we can reach principal plane. Similarly, from BC clockwise rotation by an angle 2 theta. Here it is theta. Here it will be doubled 2 theta. We got principal plane. So this will be the principal plane. Okay. The other point will be 90 degree apart, because here it is next principal plane is at a 180 degree apart, so half of this it will be 90 degree apart. So this is the method of drawing Mohr circle and calculation of the normal stress and shear stress on an inclined plane. Next, if the inputs are principal stress values, sigma 1 and sigma 2 are the input values, then how can we draw a Mohr circle? Again, draw a line, xy line. If the principal stresses are the input values, from the origin, mark first principal stress sigma 1. So we know the principal stress is the rightmost point of the circle. The minimum principal stress is the leftmost point of this circle. Okay. So mark sigma 1. This is the point corresponding to principal plane, major principal plane. Mark sigma 2. This is the point representing the minor principal plane. Measure this length. Bisect this line between these 2 points. And this is the midpoint of this line. This as diameter or this as radius. Draw a circle. So we got a Mos circle. Then from this we can find the maximum shear stress. This is the maximum shear stress value. And of course here in this problem one more thing is that what is the maximum shear stress value? Measure this length. For example, this is equal to K. This length is equal to K. K into 10 will be the maximum shear stress. And what is the location of the plane containing maximum shear stress? This is the plane of maximum shear stress. From BC to this plane, rotate by an angle alpha in counterclockwise direction. We got this plane. So from BC, rotate in counterclockwise direction. This is the counterclockwise direction. So from BC, rotate in counterclockwise direction by an angle 2 alpha. This will be the plane of maximum shear stress. Maximum shear stress plane. Okay. So what is the rotation direction? Same rotation direction should take here. But what is the angle here? We should take the double of that angle here. And here we can measure the maximum shear stress. So that is another case of drawing Mos circle. Another one, if this particular system containing this face containing tensile stress and this face subjected to compressive stress, then how can we draw? For that, here for example this is equal to sigma x, this is equal to sigma y. This is compressive in nature, this is tensile in nature. Take the tensile value in the positive x direction, sigma x, mark this point. Take the compressive value in the opposite direction, in this direction. So this is the sigma y value from the origin to this point. Then with respect to the direction, moment or direction of the tau xy, either it will be in the upward or downward. So if it is in upward, this will be the downward. Draw a line connecting this. We got the center point here. Draw a circle. Draw a circle connecting these 2 points. And sigma x, sigma x, sigma y, this is the point, 2 planes. Okay, and this is the, this distance is the, or this is the major principal plane, and this is the principal stress, major principal stress, and minor principal stress is this much, this value. This is the minor principal stress, and maximum shear stress is taken from, and this is the center. Maximum shear stress is this value. So this is another method. And if both are compressive, both should draw in the left hand side. The sigma x also in the left hand side. That is one more method. So do some problems related to this Mos circle. Maybe this is an important problem. So do different types of problem based on Mos circle method. So using Mos circle method, we can calculate any type of stresses, any stress components, even it is in inclined plane or principal stress or principal shear stress, we can calculate. And the radius, the midpoint of the circle will be, midpoint of this Mos circle will be sigma x plus sigma y by 2, and radius of the Mos circle, this is the radius of the Mos circle, and radius of the Mos circle will be the maximum shear stress. So we already developed an equation for finding the maximum shear stress of the this is the maximum shear stress value. So this will be the radius of the Mos circle. Okay, and that is the midpoint. So that is about Mos circle. And remember all the directions and the sign conventions used in Mos circle, and Mos circle should draw in proper scale, with the proper scale. Otherwise we will get a wrong answer. Okay, and this is about transformation of stress. And similar, the stress, everything we used in the transformation equations. That means here in these equations we discuss only about transformation of stress, and instead of stress, for example, in this body the strain in this direction is sigma xx, strain in this direction is epsilon xx, strain in this direction is epsilon yy, and shear stress in these directions are gamma xy by 2, gamma xy. Then what is the strain in this direction? What is the shear strain in this direction? What is the normal strain in this direction? So every time change it from stress to strain. So when we deal with the system consists of strain, the only difference is that instead of this all stress terms in this equation, write the strain terms. That means epsilon n equal to epsilon xx plus epsilon yy by 2 plus epsilon xx minus epsilon yy by 2 cos 2 theta plus, instead of gamma tau xy, this is very important, instead of tau xy we should give gamma xy by 2. This tau xy not directly replaced with the gamma xy, tau xy should be replaced with the gamma xy by 2. And we can rewrite all the equations of the stress transformations into strain transformation by replacing sigma n with the epsilon and tau xy with the gamma xy by 2. Gamma xy by 2. That is very important. And that is the transformational strain. So these are the equations of, see this, the only difference is tau xy is replaced with the gamma xy by 2, epsilon sigma x sigma is replaced with the epsilon, and here also here it is sigma t shear stress, that is also replaced with the gamma xy by 2. All the other terms are same. Here also gamma xy by 2. And for principal strain, maximum and minimal principal strain, this is the equation. We replace everything with the gamma xy. Epsilon x and gamma xy. See this. Okay, so change the equation with the epsilon and gamma xy, and this is the analogy between stress and strain transformation. Analogy. The normal stress on oblique plane is this one. Here instead of sigma we use epsilon for normal strain on oblique plane. This is tangential shear stress on an oblique plane. Here instead of sigma t, here it is gamma xy by 2. And in tau xy replaced with the gamma xy by 2. And the principal stress on principal strain are same. Here also tau max is replaced with the gamma xy by 2. Tau xy square, and that is actually tau xy is replaced with the gamma xy by 2 whole square, so 4 and 4 cut each other. Okay, so this is the analogy between stress and strain. So that is about transformation of stress and strain, and do different problems in related to Mos Circle. So here in this, actually according to your syllabus, the transformation of stress and strain is not included in your syllabus, but the Mos Circle, the two-dimensional Mos Circle is included in your syllabus. So the basic understanding of the transformation theory is very important to draw the Mos Circle. That is why I take the derive the all 8 equations and theory portions of transformations of stress and strain. So you have to study in deep about Mos Circle, but you should understand the concept behind this transformation stress and strain theory. Okay, thank you.